In this video, we're going to look at an application of implicit differentiation. The overall topic is called related rates. And as we know, a derivative is an instantaneous rate of change. And so in these problems, in related rates, we're generally going to look at the rate of something changing with respect to time. So one of the things that you'll see is instead of finding dy dx, which means we're taking the derivative of y with respect to x, what we'll be doing here is finding the derivative of y or x or whatever variable. For example, we might have dx dt. In other words, in these problems, because we're looking at them as related rates and we're taking the derivative with respect to time, whenever we take the derivative of an x variable, we'll have a dx dt left behind because we're taking the derivative with respect to time. And you're going to see that play out in these problems, and that's where your implicit differentiation comes from. All right, so let's just jump in and take a look at this and kind of see what the process is. I want you to look at a couple of things. I want you to look for the implicit differentiation. I also want you to look and think about the process and the steps of solving a related rate problem, because many students get nervous when they have to deal with a word problem. But they're really not that difficult if you just take your time and take the problem apart. So let's read through this problem. Phoebe is going east on Alamo Street at 40 feet per second. Meanwhile, Calvin is going south on Heights Street at 30 feet per second. All right, so Phoebe, as you can see, is traveling in this direction on Alamo Street. She is moving in the x direction, and they've indicated that by marking that distance with x. Her velocity, or her rate of change, is 40 feet per second. Then we have Calvin, who is traveling southward. So he's traveling in the y direction, and he's traveling at 30 feet per second. So the first thing it tells us to do, and this sheet is basically going to walk us through the process. Let x be Phoebe's distance from the intersection, and let y be Calvin's distance. Write the rates that you know and explain why dy dt is negative. All right, so dx dt, I'm going to use blue if I keep remembering correctly. We're going to use blue to represent Phoebe's distance and Phoebe's velocity and anything to do with Phoebe. So her rate of change, or her velocity, is 40 feet per second. Now again, dx dt indicates Phoebe's velocity. I don't think I spelled that right, but you get the idea. Phoebe's velocity. dy dt, now they've already kind of hinted to you that that rate is negative, and the reason that that rate is negative is because the distance between Calvin and the intersection is decreasing. So if that distance is decreasing, then his velocity is going to be negative, so we indicate that the distance is decreasing, negative 30 feet per second. So that is dy dt. That's Calvin's velocity. And since x represents Phoebe's distance, change in position over change in time is the velocity, and since y represents Calvin's distance, dy dt represents Calvin's velocity. Now, what we're interested in this problem is Phoebe wishes to determine whether the straight line distance between Calvin and her, so that distance that she's talking about, she wants to know if this distance is decreasing or if that distance is increasing. Now, if we want to determine whether a value is increasing or decreasing, then one way we can determine that is to know whether the first derivative is positive or negative. If the first derivative is positive, something is increasing, and if the first derivative is negative, something is decreasing. So we're going to let z be the distance between Calvin and Phoebe. Now remember, they're moving, driving their cars, so they're moving. Calvin's going towards the intersection, Phoebe's going away from the intersection. So number 2 says, let the straight line distance between Calvin and Phoebe be z. Write the symbol for the rate that you want, where we're looking for the change in z over change in time. So there's that implicit differentiation that's going to come into play. Now, to find the rate that you want, you need an equation relating the variables. That's very important. The first thing you want to do is take a look at the triangle. I think you can see that this is a right triangle. And so we need an equation that's going to relate, because this is called related rates, an equation that's going to relate the three variables. And I think you can see that if we have x squared plus y squared by the Pythagorean theorem, that's equal to z squared. So now we have an equation that connects all three of my variables. So now my variables are related. All right, let me do something here. So the equation that we were looking for is x squared plus y squared is equal to z squared. All right, so now that we have our equation, in number 4 it tells us to differentiate both sides of the equation. So this is where we're going to bring our rates in. Currently we have an equation that relates the distances to each other, but we need to compare the rates. So if we find the derivative, let me copy my equation down again. We have x, edit, undo, get my pen here. We have our original equation, x squared plus y squared is equal to z squared. So when we take the derivative of x squared with respect to time, so notice it says differentiate both sides of the equation with respect to t. So I have 2x dx dt. There's my implicit differentiation along with the chain rule, plus 2y dy dt is equal to 2z dz dt. Every term has a 2 in it, so I can divide everything on both sides by 2, and I'll get x dx dt plus y dy dt is equal to z dz dt. All right, so think about what we've done. We read the problem, we gathered all the information out of the problem, we found an equation that connected or related all of our variables, and then we took the derivative with respect to time. So now we have an equation that involves Phoebe's position, let's underline that, Phoebe's position multiplied by her rate. We have Calvin's position multiplied by his rate, and then we have the distance between them multiplied by that rate, and it's the dz dt that we are interested in. All right, let's see what number 5 asked us to do. So we have our derivative. Number 5 says when Phoebe is 200 feet, now Phoebe, remember, was a value of x, so I'll circle that in blue, so that's going to be an important value. When x is 200 feet from the intersection, Calvin is 600 feet from the intersection. All right, so that's going to be a y value. At this time, is the straight line distance between them increasing or decreasing, and at what rate? So the straight line distance, remember, was a z, so basically they're asking us to figure out what's going to happen with dz dt at this particular time. Now because they're moving, their velocities and their distances are changing, but we're talking about, well, their velocity is not changing, that's given, but their distances are changing. So we want to talk about this particular instant of time. I'm going to bring my equation back up from the bottom, so I have x dx dt plus y dy dt is equal to z dz dt. All right, we're going to substitute the values that we know. Remember, they told us x was going to be 200. I know that Phoebe's velocity is 40 feet per second. Calvin is 600 feet away from the intersection, and his velocity, remember, is negative 30 feet per second because his distance was decreasing. I'm looking for dz dt, and I need a value for z. Well, to find my value for z, I'm going to go back over here to my original equation. This is going to help me find the value of z, and I'm going to use the Pythagorean theorem by substituting in the values. So I would have 200 squared plus 600 squared is equal to z squared. And of course you would use a calculator to calculate that. And z, using my calculator, turns out to be 632.456. That's a rounded off value, feet. So I'm going to take that value in here. I'm going to write it sideways because I didn't leave myself very much room. 632.456. Okay, I'm going to finish up solving that. So 200 times 40 gives me 8,000. Let me change back here. So I have 8,000 plus 600 times negative 30 gives me negative 18,000 equal to 632.456 dz dt. So I'm going to add and divide. I'm going to divide that by 632.456, and that gives me z. Let's do that in green. If you calculate that out, dz dt turns out to be negative 27.3 decimal places 196 feet per second. And so since that velocity is negative, the distance between them is decreasing. Remember, when velocity is negative, the distance is decreasing. So that's the first answer, and it's decreasing at a rate of negative 27.196 feet per second. Problem number 6. Naive thinking might lead you to conclude that since Phoebe is going faster away from the intersection than Calvin is going toward the intersection, the distance between them is increasing. Do the calculations confirm, or do they refute? Well, they refute this conclusion. Write a list of things that you did in solving this related rate problem. All right, so let's go back and review what we've done here. And these are the steps to solve most every related rate problem. These are general guidelines. Number 1, read the problem and identify all givens. Number 2, write an equation that relates your variables. Now, built into number 1, I didn't state this. This says read the problem, identify all givens. Also, it may be helpful to draw a diagram depending on the problem. All right, number 2, we need an equation that relates your variables. And once you get that equation, number 3, take the derivative of both sides. Number 4, oops, let me add something to that. Erase, 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 erase. Come on. All right, there we go. Take the derivative of both sides with respect to time. Number 4, substitute given values. And number 5 is to solve. All right, now in addition to that, I want to add a few hints that will be very important for related rates. Let me move this out of my way here. All right, hint number 1. You may not, this is very important, substitute a changing value into a variable until after differentiation. Very, very important. And let me explain what I mean by that. It says you may not substitute a changing value. Well, what the heck is a changing value? Well, in this problem, Phoebe is driving, and her distance from the intersection is changing. So what I mean by that, since x was representing her distance, if you look back over here at this equation, even though they told me in step number 5 that she was 200 feet, I believe it is, from the intersection, I cannot substitute the 200 feet into the original equation because that is a value that is actually changing. They're freezing an instant of time to talk about the time at 200 feet away from the intersection, but because that's a changing value, I have to find the derivative first. So I have to go through this whole process of finding the derivative first, then I can substitute in the 200. Now, if there is a given value in a problem that's never going to change, for example, if they tell you the height of a building is 40 feet, well, the height of the building isn't going to change, so that number can be substituted from the very beginning. Any value that's changing cannot be substituted until after differentiation. And the more you do these problems, the more you're going to understand that particular hint. All right, let's take a look at a couple more and set those up and see if we understand the process. You've got your steps of how to do this. Number 1, how does, and this is also in your packet, how does the radius change? So we're looking for radius change. That's the first thing we want to identify, and usually we'll let r represent radius. So if we're looking for how fast, that is a rate. So basically they're saying find dr dt, because that is radius rate. And notice what I'm doing. I'm reading the problem and I'm breaking it down and recording the information that I need. How fast does the radius change when air is blown into a spherical soap bubble at the rate of, so they're giving me a rate, 10 cubic centimeters per second. Now look at the units of that, 10 cubic centimeters per second. They're giving me dV dt. In other words, cubic is a unit of volume. So dV dt is 10 cubic centimeters per second. So I need an equation that's going to connect radius and I need to connect volume. Those are the two variables that I need, and it's a spherical soap bubble. So I need to know the formula for the volume of a sphere. And the formula for the volume of a sphere is 4/3 pi r cubed. So volume is equal to 4/3 pi r cubed. And you may have to review some of these geometry formulas. All right, so I have I read the problem, I recorded my information, I have an equation that relates my variables of v and r. So the next step is to find the derivative of both sides. The derivative of v with respect to time is dv dt. Using the power rule on the right hand side, I get 4 pi r squared dr dt. Remember, we're taking the derivative with respect to time. I know that dv dt is 10, so I'm going to substitute 10 in place of dv dt. 4 pi r squared dr dt. Now this time they're not giving me a particular value for the radius to determine when this is occurring. They just want me to find dr dt as a formula. So I'm going to divide both sides by 4 pi r squared. So dr dt, the rate of change of the radius, if I reduce that, is 5 over 2 pi r squared. Again, we don't have a value and we don't have to put units in because they're not asking for a particular time. This is just a formula for the rate of the radius change. All right, let's take a look at another problem that will give us some values and we can actually solve it. Number 2. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So we're dealing with circles here. The radius of the outer ripple is increasing at a constant rate. So here's our R for radius, increasing at a constant rate. So they're telling us dr dt is 1 foot per second. When the radius is 4 feet, when r equal to 4, notice I'm just reading and recording, at what rate is the total area changing? So they're asking us to find dA dt. Alright, so we have a circle, we have a radius, and we're talking about area. So we need an equation that's going to connect area and radius of a circle. That's pretty easy. Area is equal to pi r squared. We have our equation relating our variables, so we're going to find the derivative of both sides with respect to time. We get dA dt is equal to, using the power rule, 2 pi r dr dt. All right, now we're going to substitute the known values. We're trying to find dA dt, so we're going to leave that alone. We know that the radius that they're talking about here is 4, so we can substitute that in place of r. Remember, that's what I was talking about. Notice we did not substitute the 4 into the equation. We found the derivative, then we substituted in the 4. The dr dt is 1 foot per second, so dA dt is equal to 8 pi. Think about what we're dealing with here. The rate of change of area. So 8 pi feet squared, because it's area. Remember, area is in square units per second. So in this pond where you have these circles, concentric circles, when the radius is 4 feet, the area of the circle is changing at a rate of 8 pi square feet per second. All right, let's do one more of these. A board 5 feet long slides down a wall. So we have a wall. We have a board that's sliding down the wall, so that's my board. At the instant the bottom, and so let's go ahead and call this X, Y, and I'll call this Z. At the instant the bottom is 4 feet from the wall, so the bottom of the ladder is down here, so when X equal to 4, the other end is moving down the wall. That's important. The other end is moving, where to go? Down the wall, so that tells me negative, and so that's the distance that we have over here. So when X is equal to 4, dy dt is equal to negative 2 feet per second at that moment. So question A, how fast is the bottom of end sliding along the ground? So they want me to find dx dt. In other words, how fast is the board moving in the x direction? All right, let's see what we have here. I think it's pretty clear that we're going to go with our friend Pythagorean theorem. X squared plus y squared is equal to z squared. The board is 5 feet long. Now, this is one of those situations, and pay very careful attention here. The board is 5 feet long. The length of that board is never, ever, ever going to change. It's 5 feet long. So instead of letting that be a variable, instead of letting that be z, I'm going to cross that out and say, well, it's 5 feet long, and in my equation, x squared plus y squared is equal to 5 squared, which is 25. That number can be substituted from the very beginning because it's not going to change. I cannot substitute values in place of x and y. I have my equation, so I'm going to take the derivative with respect to time. 2x dx dt plus 2y dy dt is equal to 0. which works out nicely. Saves me a little work. I can divide the 2's out on both sides. So we know that x is 4, so in place of x I'm substituting 4. dx dt is what we're trying to figure out. In place of y, well, if x is equal to 4, then this would be a 3, 4, 5 triangle by the Pythagorean theorem, so y would be 3. Notice I had to go back to the original equation to solve that. And dy dt is negative 2 equal to 0. Now remember, I divided the 2's out on both sides, so that's why I don't have the 2's in my equation anymore. So I have 4 dx dt is equal to 3 times negative 2 is negative 6, added to the other side is 6. So dx dt is equal to 3 halves feet per second. And since that dx dt is positive, that tells me that the board is moving away from the wall, which we are already near. Okay, so that's part A. If you need that, you can go back because I'm getting ready to get rid of it because I need to do part B and I need to use that same space. Alright, so let's go back. Let's clear that. Part B. So we have our same triangle. Our board is 5 feet long. Here, let's clean that up a little bit, make it better. So our board is still 5 feet long. We have the same scenario. This is the x direction. This is the y direction. dy dt is still equal to negative 2. And dx dt that we found, because we're dealing with the exact same time, dx dt we just found out to be 3 halves. And they said when x is equal to 4, so we had x equal to 4. We used the Pythagorean theorem to get y equal to 3. So we have all of our information recorded. How fast is the area? We're looking for fast area. So we want dA dt. All right, well, the area of a triangle is 1/2 base times height. So in this case, we would have area is equal to 1/2 of x, y. So we're going to substitute, we're not substituting anything right now. We're going to find the derivative, dA dt. We're going to need the product rule on the right-hand side. I'm going to leave my 1/2 out front. So I have first derivative of second. Remember, we're taking the derivative with respect to time, plus second times the derivative of the first. All right, so now we can substitute in our values, dA dt. The rate of change of area is 1/2 of x is 4. dy dt is negative 2 plus y is 3 and dx dt is 3 halves. So that gives me 1/2 of negative 8 plus 9 halves. And negative 8, I'm going to cross that out as negative 16 halves. So negative 16 and 9, so that gives me 1/2 of negative 7 halves, which is negative 7/4. This was a measurement of area, so that would be, is this measured in feet? Feet squared per second. And that tells me that the area of the triangle, the area is decreasing because the rate is negative, and that makes sense. If the board is moving down the wall, the triangle is getting smaller and smaller and it has less area. All right, so hopefully this gives you a good start at related rates and will help you out.